Welcome back to the Math Professors. If you're looking for content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and we're going to do some eigenvalues and eigenvectors. So if A is an n by n matrix, does there exist an n by 1 matrix that's not 0, such that A times x is equal to some lambda times x, where lambda is called a scalar, and this is going to be, lambda is a scalar, which is called the eigenvalue, and x is the eigenvector. So what I want to do is I want to verify an eigenvalue and an eigenvector. So I just need to make sure that this is satisfied, that if I do A, which is this matrix times x, that this is going to be equal to this lambda times x. So we're just checking that. So I have to show that A times x is equal to some lambda times x. So A is going to be this 2 by 2 matrix, 4, 3, 1, 2. And then we're going to multiply by this matrix x, which is going to be 3, 1. And doing this multiplication, 4 times 3 is going to be 12 plus 3 times 1, which is 3, and then 1 times 3, which is 3, plus 2 times 1, which is 2. So what we're going to get is we're going to get the matrix 15, 5. Now I just need to make sure that this is equal to this, this lambda, which is 5 times this matrix 3 times 1. And what we can see is that 5 times 3 is going to be equal to 15, and then 5 times 1 is equal to 5. So yes, this is satisfied. All right, let's talk about really what an eigenvalue and an eigenvector are. So what I'm going to do is I'm going to look at this in terms of its components, as a vector. So this is going to be equivalent to that vector 3, 1. So 3, 1. So what we can see is we get this vector that goes 3, 1. And what happens is when you multiply a matrix times a vector, what it's going to do is it's going to transform this vector. And for it to be an eigenvector, it needs to transform it so it doesn't change its direction. So what we can see is when I take this A times this x, what I get is I get 15, 5, which is actually just 5 times the original vector, which really means it's just a stretch of that original vector. So it's a stretch by 5 times. It's going to look like this. So now it's going to be 15, 5. So eigenvalues and vectors, tons of applications of these things. So let's think about it as far as revolutions go. So let's say I have my coffee cup here, and I have, say, all the normal vectors come off this. So on the side, if I do a rotation, what we can see is that, again, this is essentially taking this thing and multiplying it by a matrix, which will give us some kind of rotation. It's a special matrix, and we'll probably get to that in one of our videos. But as I can see through a rotation, that's definitely not an eigenvector because it's changed directions. But if I put it on the pole and I spin this, what I can see is that this is no longer changing direction. It's not even stretching it. Really, in this case, lambda is just going to be equal to 1. So if you think about like satellites that's orbiting the Earth and they have rotational spin, you really just want to make sure that they're always pointed in the same direction. You're really looking for their eigenvectors. So how do we grab these things? So we're going to come up with a characteristic equation that will help us find these eigenvalues and eigenvectors. So we're finding the characteristic equation for these eigenvalues. Really what I'm trying to do is I'm trying to make sure that, A times x is equal to some lambda times x. So set up the characteristic equation. We're going to set this equal to 0. So I'm going to subtract this matrix to this other side. Now, what I want to do is I want to be able to factor out an x, but since x is a matrix, I can't factor it out because I'm going to be left with a scalar here. So I have to multiply lambda times I first, minus A times x. And now when I factor this this x out, this is now still a matrix. So being careful with our matrix algebra or arithmetic. So, and this is going to be equal to 0. So really what I'm trying to do is I'm trying to find solutions of this equation, but really I'm actually trying to find the one that will give us infinite solutions. So that'll happen when the determinant of this thing is equal to 0. So really the characteristic equation is just grabbed by the determinant of this coefficient matrix is equal to 0. So let's use this characteristic equation, and you'll actually see the reason why we call it a characteristic equation is because this is going to spit out usually, well, it's going to spit out a polynomial, and it happens to be the roots of that polynomial are going to be your eigenvalues. So very similar to like differential equations when we talk about the characteristic equation of a differential equation, it happens to be the roots are important. So very similar here, the roots are important. So we're going to determine the eigenvalues and the eigenvectors of this matrix, and we're going to do this by, by that characteristic equation. So what I need is I'm going to need the determinant of lambda times I minus a is equal to 0. All right, so in order to set this thing up, I'm just going to write this in this form. So the determinant. Now, lambda times I is going to be lambda times, since this is a 2 by 2 matrix, this is going to be 2 by 2 in terms of I, minus A, which is going to be this 2, 5, 4, 3. And I need that determinant to be equal to 0. Simplifying this is going to be lambda's on the diagonal. And condensing, so subtracting these two, we're going to have lambda minus 2, 0 minus 5, so negative 5 in that component, 0 minus 4, so negative 4 here, and then lambda minus 3. And remember the determinant equal to 0, so when I find the determinant of this, multiply that main diagonal, so lambda minus 2 times lambda minus 3 minus negative 5 times negative 4 is going to be 20. Is equal to 0, and then you can see that this is just going to be a quadratic equation. So lambda squared minus 3 minus 2 is minus 5 lambda, plus 6 minus 20 is equal to 0. So what we get is we get lambda squared minus 5 lambda equal to 0. Now I have two solutions here because this thing factors lambda minus 7 and then lambda plus 2. So we'll call it lambda 1. The first eigenvalue is going to be 7, and then the second one is going to be equal to negative 2. Now we're going to use these to find our eigenvectors, and you can see why we wanted this, because it's going to give us a system of equations that has infinite solutions. And let's show you. So really what I'm trying to solve, I want to solve is this lambda I minus a times x is equal to 0. And now that I made the determinant of this equal to 0, this is going to have infinite solutions. So when we set this thing up, this is going to be, I'm just going to write lambda I. We know that this is going to be lambda 0, 0, lambda minus 2, 5, 4, 3 is going to be equal to 0. I'm going to write this in augmented form. So times x is going to be equal to 0. So setting this up, this is going to be equal to lambda minus 2, and then negative 5, and then 0, and then minus 4, so negative 4, and then lambda minus 3, times the matrix x1, x2 is going to be equal to 0, comma 0. So augmented matrix form, it'll help me row reduce. So I'm going to have lambda minus 2, minus 5 here, 0, and then minus 4, lambda minus 3, and then 0 here. So using this, I'm going to find these two eigenvectors. So first we'll put in lambda 1, which is equal to 7. So lambda 1, which is equal to 7, we're going to get this matrix here, 7 minus 2, which is going to be 5. This will be negative 5. We have minus 4, and then lambda minus 3 is going to be equal to 4, and this is going to be 0, 0. Now remember, this is going to have infinite solutions. It means that one of these rows is going to be a direct multiple of the other one, and what I can see is if I multiply that bottom row by by 5 over 4 or negative 5 over 4, I'll get the top row back. So when you do row reduce this thing, you're just going to get this 5 minus 5, 0, and then 0, 0, 0. And if you want to even simplify it more, you can divide the top row by 5. So remember what this matrix is it's this times x is equal to 0. So really what that top row tells us is, I'll write it up here, this top row tells us that x1 minus x2 is equal to 0. And remember that x1, x2 is going to be our eigenvector. So x1 is equal to x2. So I can rewrite our eigenvector x as x1, x2. Now x1 is equal to x2, so this is the same thing as x2 over x2, or you can say x1, x1. And when I pull out that common factor, we're going to get 1, 1 here. So this 1 comma 1 is going to be our eigenvector. So we'll say that this is going to be x. Yeah, we'll just leave it that way. So this is going to give us the vector 1, 1. And what does this one give us, the vector? So doing the exact same thing with this, now we're going to do it for lambda 2. Which is equal to, actually what I'm going to do is I'm going to plug in positive 2. Let's say I got that wrong. And I just want to show you what happens, like if you know you got one of these eigenvalues wrong. So let's say I plug in 2, and we'll fix it immediately. So 2 minus 5 minus 4, and then so this is going to be 0, and then this is going to be negative 1. Now what we can see is that these rows are not multiples of each other. So you're not going to have that infinite solution, so you know that you plugged in the wrong one. So if I plug in negative 2, what happens here? So negative 2 is going to be equal to minus 4, minus 5, 0. This is minus 4. This is also minus 5 and 0. And what we get is that bottom row will go away. And if we want to make the first one 1, what I can do is I can divide everything by negative 4. So this would be 1, this would be 5/4, this would be 0. So now our new matrix X, which is going to be x1, x2, and what this says is x1. I'll write it up here. Sorry about the out of room. x1 plus 5 over 4 x2 is equal to 0. So x1 is going to be equal to minus 5 over 4 x2. So this is going to be equal to minus 5 over 4 x2, and this will also be x2. Now if we pull out that common x2, what I'm going to have is we're going to have these are going to be in rational form, and they prefer to have them in integer form, so I'll fix this in just a minute. So if I want to put this in an integer form, I just multiply everything by 4, so we can see 4x2, and this is going to be a minus 5, and this will be 4. So this eigenvalue gives you this eigenvector. And then similarly, this eigenvalue gives you this eigenvector. And remember that you can check this. You can check that a times x is equal to lambda times x. So let's just show that for one of them, and then you can do the other one yourself. So what I can show is that, remember, if it's an eigenvector, this happens, right? So a is going to be 2, 5, 4, 3 multiplied by x. In this case, let's do the let's do the 1, 1. It's so much simpler. So then 2 times 1 plus 5. So this is going to be 7. 4 times 1 plus 3 times 1, which will also be equal to 7. And remember, this is supposed to be 7 times that 1 times 1, and this indeed is 7, 7. So this is the eigenvector value mixed with that, match with that eigenvector. So let's do one more that's a 3 by 3. It's just a little messier. I'll show you how to find the 3 eigenvalues. I'll show you one eigenvector, and I'll leave the other 2 eigenvectors as homework. All right, so find the eigenvalues and eigenvectors for this 3 by 3, and I threw a bunch of zeros in it to make this quick for us. So what we know is that we're just finding the determinant of lambda I minus a, and make that equal to 0. So the determinant of lambda I, since this is going to be a 3 by 3, we're going to have lambdas on our diagonals. And then we're going to subtract our A matrix, which is 4, 0, 0, 0, 0, minus 3, 0, minus 2, 1. Find its determinant, set it equal to 0. So this is going to be lambda minus 4, 0, 0, 0, lambda 3, 0, 2, lambda minus 1. And set this equal to 0. So what we can see is that for this characteristic equation that this is, it's 3 by 3, so we're going to have a cubic polynomial here. So simplifying this, since it's a 3 by 3, I'm going to choose this row 1 expansion. So lambda minus 4 times, this thing is determined, this 2 by 2 on the bottom right. So times the determinant of lambda 3, 2, and then lambda minus 1. And then, minus 0 times the determinant of these things. So 0, 3, 0, lambda minus 1. And then finally plus 0 times, and I know these are 0, but just in case you have one that is not as friendly. So, since these are 0, those will be gone. So this is going to be equal to lambda minus 4 times, lambda times lambda, this is going to be lambda squared minus lambda, and then minus 6 is equal to 0. And actually, it's already kind of factored for us. Usually, if you had all these things, you'd have to expand them, combine like terms, and then factor that cubic. But I've already got a linear factor here, and I can just pull out this other linear factor. So lambda minus 4, this is lambda minus 3, and this is going to be lambda plus 1 is equal to 0. Is that true? That is not. Is that true? Sure is. Okay, so now I have lambda 1, which is going to be 4, lambda 2, which is going to be 3, and then lambda 3, which is going to be equal to negative 2. So let's do 4. We'll do this one, and then you can do the other ones. So 4, remember what we're doing is we're trying to solve, this equation, lambda I minus a times, our x is equal to 0, and we know that these are going to give us infinite solutions, so one of these rows are going to disappear. So when I set up that augmented matrix, we can see that we're really going to have, we'll just do it by hand. So lambda I is going to be lambda 0, 0, 0, lambda 0, 0, 0, lambda minus a, which is over here. What you're going to, we already have it right there. So 4, 0, 0, 0, 0, minus 3, 0, minus 2, 1. And we're going to multiply this by, this entire thing by x, but in this case, x is x1, x2, x3, and then we're going to set this equal to, 0, 0, 0. So simplifying this, just getting that augmented matrix, we have this joined with that 0, 0, 0. So lambda minus 4, 0, 0, and then this is 0. And then 0, lambda 3 with this 0. And then finally 0, 2, lambda minus 1 with this 0. Plugging it for lambda 1 is equal to 4. So what we're going to get is 0, 0, 0, 0, 0, 4, 3, 0, 0, 2. Plug it in 4. This is going to be 2. And this is going to be equal to 4 minus 1 is 3. sure we have all the things. Okay, so I'm just going to make this the top row. I'm just going to interchange these rows. So I have 0, 2, 3, 0. And then 0, 4, 3, 0. And these are all going to be zeros at the bottom. So remember what we have here is it's going to be infinite solutions. So I'm just going to set this thing up. So the top row says 0x1 plus 2x2 plus 3x3 is equal to 0. And then the bottom row says 0x1 plus 4x2 plus 3x3 is equal to 0. And your goal really is to be able to write these things in, just solve one for one of the other variables. So I want to, I'm just going to isolate this how do I do this? I can clear x3. I don't want to do this. So I can write this as 4x2 is equal to minus 3x3, and then plug that in here. So pop this into this spot. So 2, actually I'm going to have to solve that. So 2x2 is going to be minus 3 halves x3. So plug that in here. So 2x2, this is going to be minus 3 halves x3 plus 3x3 is equal to 0, which actually proves that x3 is equal to 0. And then x2 is also going to be equal to 0. So then x2 will also be equal to 0. So what we get is we get the vector x1, x2, x3 is going to be equal to, these two are zeros. I should have parameterized this, and then x1 will just be x1. I should have wrote these things as t's, but it's too late now. It doesn't really matter. So if I parameterize it, you just let x1 equal t. So then this would be t 0, 0. So then factor out my t, I'm going to get 1, 0, 0. So this eigenvalue comes with this eigenvector. And the other ones are done very similar. Remember, you're going to get infinite solutions. You just you parameterize them, and then you solve. So if you like the content, subscribe and share. Thanks.